All right, hello, welcome everyone. It looks like there's just a couple people on today, but we're going to record this and so people can watch in recording. And welcome to today's web seminar. This is part four of our solar electric investment analysis web seminar series. And we're going to be talking about modeling considerations and optimizations in the system advisor model today. This web seminar is sponsored by the North Central Region Sustainable Ag Research and Education. And this is part of a grant that we're trying to train the trainers. And so instead of going directly to the end users, we're trying to train people that are working with those end users. And so in this case, our audience has been kind of financial professionals, and that's what we're focused on for this series of web seminars. And other ones we're focused on extension educators and other ag professionals. So the four web seminars that we have set out, and we're in part four now, and so we're going to go over some advanced modeling things in the system advisor model. But there's a couple ways you can get more information. You can obviously rewatch these in recording. We have these recording; they're up on YouTube, and also, you can see on the left, there is the Solar Electric Investment Analysis Series. That is actually a publication that's in the SARE toolbox, the Sustainable Ag Research and Education toolbox. And it's a 6-part bulletin that basically does these 4 web seminars in kind of a 6-part bulletin series that we have just updated recently. And so it'll walk you through all the steps that we've gone through for this.
And just as a reminder, John, just a note, we will be sending out a follow-up email sometime this week with direct links to all 4 of the video link postings, so that you can just have a direct access to those, as well as a link to the toolbox that has the bulletin. And in addition, in that email, John and I are going to include an evaluation tool just to evaluate the effectiveness of this workshop, and try and get your feedback on what'd you like, what would you have liked to see that wasn't included, or how we could improve this. So look for that in the coming days as well.
All right, let's move on to our tool today. And are you seeing the SAM model there on the screen, Eric?
Yes. Yep. Everything looks good.
All right. I wanted to just make sure because it didn't look the same to me. But I've downloaded the SAM model. When you download the SAM model, you're going to end up registering. You register with an email address, and they give you a key code. Every time you open it, it basically just sends the National Renewable Energy Lab kind of a ticker that says somebody used the model. And they do that so they can keep track of how much it gets used, and it keeps them in funding so that they can keep doing new updates and things like that. And so that's really what that's for and why you have to register. You can sign up for updates if you want and get email updates about it, but you can also not get those. And so then they put alerts on when they've done updates and things like that. It looks like they're looking for a new software developer for the project. We're going to open a project file, and we're going to open the one that we ran last week, which is our Ohio swine barn case study. And it's giving me an error about the weather data. I'm not quite sure why it does that sometimes, but in recent times they've had a little bit of error messages with weather data. It hasn't caused too much of a problem, but the Upper Sandusky, Ohio weather data is still there, and it should be working fine. I checked it earlier. Remember that we ran 2 examples last week, an aggressive example and a conservative example. We're going to mainly stay with this conservative example this time. It's kind of our realistic run of what could happen. I wanted to give you an indication. Let's just scroll through the tabs again to make sure that everything looks right and that we know what's in each one. We won't play with them very much, but system design, we're just laying out how big is our system, what direction does it face, what is the angle it tilts, things like that.
John, can I pause you for a second?
Please.
As you're there on system design, just a quick reminder. We have a relatively small group on the webinar today, so this part of the series can be very much interactive. So if you have any questions about what you're seeing on the screen as it relates to the model, or how if we would change a certain input that would impact something, feel free to unmute yourself or write something in the chat box, raise your hand. There's no reason that you guys can't unmute yourself and participate in this session as well, and we can make it a little more interactive.
All right. We're gonna that's very good, and we can make those changes, but we can also run multiple changes all at once, and I'll show you how to do that in a little bit with parametric analysis. The system cost, we remember zeroed everything out, and we used a cost that was kind of like we got a bid from an installer, or so we got a quote, and so that's where we got our $2.13. That's the total installed cost. Remember this example, it was tax exempt, so we don't have that tax included. But a lot of times when I get quotes in Nebraska, we're not tax exempt, but they just include taxes in their quote. So I have to recognize that I don't want to add taxes again to that. Lifetime, we're just suggesting that the degradation factor is there. Financial parameters, this is one where we spend a little time, and I want to make one note of something we changed. And from last week, we had a property tax rate of 4%, and that was correct. But we looked at a little closer at the tax rate for Ohio, and it's only assessed at 35% of its value. So we changed that. That's going to make our economics look quite a bit better because our taxes aren't as high. I think if we remember, we were paying $2,000 a year in taxes on this $50,000 system, and that seemed a little high, and it is. And so that's come down. That's going to look a little better. We are currently running it as 100% debt, and part of the reason we chose 100% debt is that there are, at least in Nebraska, and there might be in Ohio, there are some state funding opportunities where you can get low interest loans at 100% debt. If you can't get 100% debt, we would recommend changing that. So you want to run that as a real example of a system. And so we may actually end up changing that to run it at a lower debt fraction.
And one example of that would be, the USDA REAP program has a low interest loan guarantee program that will cover up to 75% of the project. So it won't go in that instance. You would want to change that. So
we could actually, that might be a fun parametric analysis, our debt percent. We may try that. That might be an interesting one to see how that debt percent influences some of the factors that we run. We're running a 6% discount rate with a 2.5% inflation rate. So just to see where we're at. The incentives, it's really only getting the federal tax credit. That's all we've signed up for at the moment. And then we have our situation of electric rates put in. And maybe a little later, we'll talk about more about detailing some different types of electric rates and things like that. The load is, we use monthly values to put in our load for our farm. And when we get down and we hit simulate, it's going to calculate what we came out with last week. But again, we had about an 18 or 19 year payback last week. Now we're seeing this 12.7 because of our taxes, our property tax difference, that 35% of assessed value versus the 100% of assessed value. So it's looking a little better. And this is the correct answer. Probably last week was a little incorrect. And that's what can happen to you if you get the numbers wrong a little bit. Things are looking a little bit better. We do have a positive net present value with our 100% debt. And we have a discounted payback that's over 25 years, NAN. So kind of what's going on a little bit. We can see that we have a little excess generation over here on this slide. This longer blue means there's some excess generation. And if we made that a little smaller, we'd have a little less excess generation. I'm just going to go through just one of these right now. I'm going to type in the cash flow. Now we're starting to see where is our money going. And I like to start by looking here. Our O&M is $360 a year in year one, $719 for our property tax, and $256 for our insurance. And so we're starting to kind of see where we're spending that money. We can also start to see if those look a little high. And that's where last week when I looked at that, I saw $2,000 some in the property tax. And I thought, oh, we need to double check that number. It seems a little high. Now, last week, Eric was running the system advisor model on a Mac, and he could save as a CSV file and open it in Excel. But when you run it in a PC, you can send it to Excel, or you can send it to an Excel with equations, and that can be powerful if you're really interested in how they calculated some of these values, because it'll download it in Excel, and I can click on one of the cells, and it'll actually tell me the equation of how it calculated that. And so I can follow the leads and figure out, are they including taxes? Are they not including taxes? All kinds of things. So that can be powerful when you're trying to interpret what's going on. Let's go back to our summary, and we're going to run a couple of optimizations here that sometimes we use early in system design and early in system when we're trying to look at a system. And that's down here in the lower left-hand corner, and parametrics. And the parametrics is I'm going to run a whole bunch of runs all at once. Instead of going in and changing the pitch angle 10 times to run 10 different, I'm just going to run them all at one time. So I'm going to hit my parametrics, and I'm going to go to quick setup. And I'm going to clear this out. This is where it looks like when you start, it's going to be clear. So what I'm adding is my variables, and I'm going to add variables in. So I'm going to start with a simple variable of the tilt angle. And that is the angle that the solar panel array is tilted. We're going to assume it's still facing south, but maybe we're going to look at this as a ground mount system. And what is the best tilt angle for my location? And so we're going to try to optimize for tilt. This is a little bit about system design, but also tells us a little bit about, could we be producing more electricity? And again, electricity is where we get our value. So we're going to hit OK. And now on tilt, we're going to analyze it across a tilt angle from, let's say, 10 degrees to 90 degrees in 5-degree increments. And it's going to now run our different scenarios here. And so 10 degrees would be fairly flat, 90 degrees is almost straight up, and we're going to run those. And it's going to input our different ones in here, and then we can select what output. And then our output is, what do we want to optimize for in this case? And so we can search through these by going to plus and looking through all of them, cash flow, batteries, things like that. We can optimize for all those, and we could optimize in this case for maybe payback or something like that. Which angle gives us the best payback? That might be interesting or important, but in this case, let's just look at annual production of energy, because in some ways that's what we want to know when we're looking at tilt. Which one gives us the most energy in the year total? And so this is in kilowatt hours, and we're going to then, so we have our how many runs we're going to do. I'm going to pull that down a little bit if I can, because I think we got one more that's down there. Yeah, there's a couple more. And then we're going to hit run simulations. It's going to run 17 simulations in about that long, and it's going to give us a graph. And now we're able to see that really this number 6 run in our chart looks like the highest. We're going to double check that up here. Our number 6 run is our highest number at 31,840 kilowatt hours. And so we've just decided that if we had a ground mount system and we're trying to optimize for pitch, 35-degree pitch angle is about where we want it to be for upper Sandusky, Ohio. And so every time you pick a different location, this is going to be a different number. So this optimization isn't perfect for you. It's perfect for our scenario uniquely. And that's generally how we run a parametric analysis. And we can start running parametric analysis for things that, from a financial standpoint, that might be more interesting. So let's go back to our quick setup and we'll clear this out. And we'll clear out our energy output here, and we'll just turn that off. And so now we're basically clear, and we're going to run a new parametric analysis to learn about something that's a little more interesting from a financial standpoint. So let's try to decide how big our system should be. And so we're going to add, and we could look through, and it's probably in PV watts is where that is. There's array type, azimuth, shading, soiling, system nameplate size. There it is. The other thing you can do, and this is what I do typically, you just type in size. And you can start to find things just by words that are in there. So system nameplate size is what we're interested in. And then we're going to edit how big it is. Remember, we modeled this as a 24 kW system. And a 24 kW system has, I'm trying to think about that a little bit. That might have about 75, 80 solar panels, just to give you a little bit of a sense of size. But we're going to model this from pretty small, maybe 6 kW, which is a fairly small system, to maybe 48 kW in maybe 3 kW increments. And you can do it as detailed or not as you want. And now we have all these different runs with different sizes. So we're going to make, now we have 15 different runs from 6 kW to 48, and our outputs, we want these to be financial outputs. So how about we have an output of payback? How do we could try to optimize for payback period, but we're financial people, and we want something that's a little bit more that includes the time value of money. So how about net present value? And so now we're going to look at net present value and payback period. And we're going to run our simulations. It gets those all run. And what we're finding out is two things in this particular run. And that is, if we start over here on the left or on the right where our payback is, that our payback is that 12 years until we get to just over 12 kW. So run 3 so it's 6, 9, 12 kW is number 3. And somewhere between 12 and 15 kW, our payback goes up just slightly. So optimum size from a payback period is somewhere between 12 and 15 kW. Would give us our lowest payback. After that, our payback gets longer. And the reason is, if we want to think about it, is our net excess generation starts getting to be more, and more of our electricity is worth those lower 5.5 cents versus 12 cents. And so that's where that starts to happen. Now, based on the time value of money, though, it's a little different. It's a little different story. And so we're seeing a net present value continuing to increase until we get to about 30 kW, and then it starts coming back down. And so if we're optimizing for net present value, it'd be about a 30 kW system. Now, this is a little bit complex because this is the net present value of money that's borrowed or 100% debt fraction. If we change that debt fraction, it's going to change things a little bit. And I think that might be fun to try this out a little bit with the debt fraction as well. And so maybe we should try that out. So let's go to our inputs, and we did it by size. So instead of running size and debt fraction and getting like huge amounts of data and getting it all crazy, let's just run it with debt fraction. The debt percent, and let's go back into quick setup, and let's do it in quick setup because it's a little easier to do in here. I think we could just type them in to different things, but it's easier to go through this edit where we can say we want to go from 0 to 100% in maybe 25% increments. And there we have that. And now we're going to have our net present value and our payback. And so we're going to decide now we're back to a 24 kW system, which is the system we ran. And we're analyzing this across the debt fractions. Should I borrow this money or shouldn't I? And what we're seeing is in this case, that the payback does not change across. The way we calculate payback, it doesn't take into account the time value of money, and the payback stays the same no matter if we borrow the money or don't borrow the money. In the case of borrowing the money, we do see that we get negative net present values if we have 0% debt fraction, and we have good high net present values when we borrow 100%, and that is because of it is cheaper to it's a cheaper source of money to borrow it than it is than equity. Equity is more expensive than the cost of borrowing. And so that's kind of a scenario situation that we have that we don't want to get confused over and think that the net present value is huge, and then I change my debt fraction to 0, and I'm going to have that same net present value. And so in this case, I've got a negative, almost $6,000 net present value if I use cash, and I've got maybe a negative $2,000 net present value at 25%, and I have a positive 1,000 when I have, actually here's the numbers, positive 1,600 when I have 50% debt. Now, the other thing that tells me, well, that debt isn't in here, but
the other thing to keep in mind here, John, is this analysis here is based on a model that in our case study here, that we sat down with our farmer, with the client, and financial advisor, and you said, you know what, we're confident that the discount rate should be 6%. We think that that's the return that we could get on cash that we have from cash on hand. And so as you change that discount rate, that's obviously going to influence these results.
This is really important, and we've struggled with this for quite a few years, with this idea that when we do this model, how confident in it are we? And we really realize that it's very sensitive to discount rate, and we have to be very confident in that discount rate. And so we are suggesting that we're confident in our 6% discount rate. That doesn't mean it's right for you. It just means that we're kind of making that assumption that we're confident in our 6% discount rate. It could be different for everybody. And there's a lot of discussion in the world of investments about discount rate, as you probably know, but one of them in solar is that if I have an investment that I can't turn around and remonetize, like a long-term solar investment, I may want a higher discount rate to try to deal with that risk. And so there's some of that discussion out there as well.
And I'm curious to hear feedback from those on the call here. So, I mean, if you were modeling this for a client, what discount rate would you be comfortable with? If anyone has any thoughts or ideas, feel free to just type them in the chat box. So, John, when you're done with the modeling here on our debt fraction, we did have a question that I think would be worth maybe revisiting. Okay. As a group. So, and it goes back to your first parametric analysis on the tilt.
Yep.
So John had a question. How often would you run the tilt calculation per year to optimize the kilowatt hour output? And I have a couple thoughts there. If you want to jump on it, go ahead. Or
no, you go ahead and get us started, and then I'll think through.
So the first thing I guess that I to point out is, when we're running that parametric analysis, Sam is looking at that from the perspective of our output in that parametric analysis was annual energy production. So it's looking at what is the optimal tilt to maximize kilowatt hour production over a 12-month period. Now, I think what John's question is, and John, feel free to jump in if you need to clarify, but I think his question is looking at, well, how do you figure out what tilt would optimize during certain months of the season? And
yeah,
it's something where I was thinking maybe you could show, and it would go back to the summary page, and you can actually look at some of the tables that would show, monthly production, monthly kilowatt hour production. I don't know that it would necessarily be in parametric analysis, but you can see that monthly production from a system and export that information into Excel as well.
We could do that. The other thing that I was thinking about, I'm going to go back to our first week here,
because and I want to frame up the reason that John's question in the chat box to me is an important one, just for everyone else on the call. So there may be certain operations where you say, boy, we use a ton of electricity, say in the winter for heating, and we don't use anything in the summer or very little in the summer. So you might want to optimize your tilt for the winter months, or vice versa. Maybe you use a lot for ventilation and you don't use a lot of electricity in the winter.
Yeah, that's a really good way to look at it, is to think about optimizing for the time of year. The other thing is you could optimize for time of year when value of electricity was higher if you had an electricity rate that varied throughout the year. And so you'd say, well, summer is higher electricity rate. Maybe I want to optimize for summer. This is a chart that I created using the parametric analysis, where I ran this with azimuth's direction, which is the direction it faces, from 0 to 350. And I also ran a tilt angle from 2 to 90. And then I just put that in a chart. And so in this case, I ran that. And now this is for fixed tilt systems. But what you have in some ways on what Eric was describing is that if you have a system that doesn't have a fixed tilt, you're tilting it through the year to maximize this. This is maximizing it for one fixed tilt. But if you were trying to maximize it by changing it, you could maybe try to decide how often you change it. That'd be an interesting parametric analysis to run. You'd say, what tilt angle during what month of year would I want to be? The answer is that if it's constantly changing, it's going to give you the best, but you could try to say, well, I want to do it only 4 times a year. When should I do it? You might be able to figure that out. What I was looking at here was seeing if I could model, just looking at it from a system of single axis or dual axis tracking. And I think the only way I could do that at the moment is to go back here to system design, and I could just simply say, instead of this being a fixed system, I have, let's say, one axis tracking. One axis tracking faces east in the morning and changes to west in the afternoon. And remember, that's going to give us some. Let's double check our numbers first. And so 3,800 kilowatt hours is what we're using on a fixed system. And now let's go back and go to one axis tracking just to see what it does. Again, this is where we're running this one at a time, but we gain almost 8,000 kilowatt hours a year to do that. And our payback went from 12 to 10 years, and our net present value jumped pretty significantly. So this is where we have to, in some cases, decide if the value of that one axis tracking is worth the added cost, because one thing we didn't change when we changed to the tracking is the cost of the system. The cost of the system would have been higher. So we got to be a little careful where we don't just run simulations and assume, well, everything costs the same to do the tracking, and not. It would.
And I know on utility scale systems, the benchmark cost on utility scale systems is $1.06 per DC watt for fixed tilt systems versus $1.13 per DC watt on single axis trackers.
Yeah.
Now, I don't know that number off the top of my head for commercial systems.
It's gonna be higher, and part of that is that they have so many economies of scale when they put those monstrous systems in, and those economies of scale. I don't know how big you have to be to get those, but my guess is you have to be in the megawatt scale before you start to get those prices. So, good question. I'm going to talk a little bit about a couple more of these tabs up top that can give us some, interesting visuals of what's happening and what's going on. And so I'm going to click on the profiles, and a couple of them I'm going to do here is electricity load in year one. And so this is every month in a year. And it's basically saying this is how this particular farm is using electricity. Now, this is the model's estimate of how it's using electricity, because remember, we put in monthly data. And then it's suggesting that a day in August looks like this. This is kind of the average day in August. This is the average day in December, the average day in October, et cetera, et cetera. And so we kind of have these different average days throughout the year. And then if we want to compare that, one thing we could compare that to is how is our system then generating compared to our average day? And so this is what our system might look like, where the fun thing about this particular chart is this is a day in July. And we can say, well, did I send any electricity to the grid on this day? Yes, I sent everything between above this blue line, but under this orange line in this area, I sent to the grid that day. But did I send anything net to the grid that day? The answer is no, I actually used from the grid. And the way I can kind of look at that just from a graph standpoint is I add up these blocks. I got about a half a block here, got about a half a block there, and a quarter of a block. So I've got 1.5 blocks, 1.25 blocks on this side under the blue and above the orange. And on this side, almost about the same. I got about just over a half, and a quarter. So I've got almost 2.5 blocks under the blue and above the yellow, but I've only got about 1.25 or half, about 3/4 of a block up here. So I've got 2.5 blocks minus 3/4 of a block. That's going to give me where I'm actually using more electricity during this average day in July than I am generating. Now, you're not necessarily going to do the math because the system can do all that math for you, but it's a good way, fun way to visualize it. And so where I'm getting some net excess generation is where the area under the orange and above the blue is larger. So November and December and January are going to be those months where I'm over generating and having that net excess generation. So it's kind of a fun visual to kind of look at. Another one that I picked out that I thought is kind of fun and tells a little bit of a story is if I look at electricity from the grid. Remember that one I had before was the load and the system. Now let's actually look at how that solar affects the electricity from the grid. And this is somewhat of a similar chart, but you can start to see that in the morning, I'm using electricity, and then all of a sudden it comes up to a peak and then drops down. Well, what's happening is that solar is coming in and taking that load, and that's why it's leaving that middle of the day load very low. So we can add that in as well. And so now we can start to see where we have the opposite thing happening, where the solar is coming on, it's taking that load from the grid, and then that grid electricity is coming at very low levels, and the solar then is taking that up. What's kind of fun about this is you can just kind of imagine what's going on in a particular system at a particular time of day. The other thing you can kind of think about is that when is electricity valued in a time of use rate? If that electricity value is highest during the middle of the day, that's also when I'm generating that electricity. And so that time of use rate might actually give me some extra benefit in that sense.
The other thing, John, that this could help you visualize is, anything that's within your solar production. I'm not sure if you can see my cursor or not.
No.
So anything that's below the blue line within your orange bars, that's full value, right? That's retail rate electricity. Right. Whereas anything above the blue line, we need to, kind of be conceptualizing that, okay, this is a month where we need to be thinking about what's the value of excess generation.
Right. I was actually thinking about, kind of this interesting idea where actually that would actually be more true, Eric, for the visualization I had a minute ago, which is the bill load, electric load year one in KW. Get my units the same here. System power in KW. Now this is all worth retail rate under here. Everything below the blue and above that's all worth retail rate. This may not be worth retail rate in a PERPA type of a system, in a system where I don't have net metering. So on the previous one, I was a little confused for just a minute how they were doing this calculation when I pulled these other two up, and that's not it. Electric from the grid, electricity from the solar. I got too many things going on. Electricity, get rid of load. Now I got to click those in a different order, so I'm back to my original colors here. Electricity from the grid, electricity from the system load. I feel like this number should theoretically go to 0 down here in the middle of the day, because where I'm generating all my energy from the solar. And that's true, except for remember, this is an average day for, in this case, the month of March. So that being an average day, it doesn't go to 0, but on an individual day, it would probably go to 0 if we looked at an individual single day. If we have any questions, we can do that. Otherwise, let's go play with this electric rates for a moment. One thing that was the question the other day was, how do we do time of use rates? Now, we could try to download from a utility that had time of use rates. And if you guys have an example of a utility we want to pull up a load from, I'd be willing to pull it up. But if I was trying to make my own rate, I might say there's 3 different entries here, and period 2 is my time of use. And what's happening is in the summertime, really between the hours of 1 and 6 during the summer is my period 2. And that's true on the weekdays predominantly, because that's the business week. And maybe there's 1 tier during that. It's for all the electricity, and that is all worth 18 cents. It's much more expensive. My salary point is 0.055 during that same time, something like that. And what we have then is a time of use. Now, these can get really complex as we get into certain parts of the United States, where that time of use could have all kinds of other things. It could be for 1 hour or something else. Maybe even, let's just build another fun one here. Maybe we say, but really during the peak, this is our period 3, when everybody comes home from work. Everybody comes home from work at this time, and this is our period 3, and this is going to get really expensive in here. And that's maybe 23 cents. And so now what the utility is obviously doing in this case is 2 things. One, I think they're trying to make their money during the time when electricity is very expensive. But the other thing they're doing is they're trying to influence their customers to maybe switch their hours a little bit. They're saying, if everybody turns on and everybody's running hard at that time, we have to have every power plant we have on, including the most inefficient and the most expensive. But if you were to switch your work hours maybe and try to run during the morning, we're going to give you a good deal. And so you're going to pay 12 cents for that electricity if you run an extra shift in the morning versus an extra shift from 4 to 6 p.m. And so there's obviously things that are influencing, and we can build those into these models in any detail we want. What we really try to do is not make these numbers up. We try to base these on the rate schedules that we're finding out there. And again, the best way to find a rate schedule is to figure out what number your rate schedule is from your electric bill, go onto the website of your utility, and then go into their rate schedule. They'll have, almost every utility will have those published in all their detail. Sometimes they can get a little complex, but hopefully you can figure it out. The other way that you can do this is simply by downloading rates. So do you know any time of use rate structures in Ohio, Eric?
We do not. I do not. I don't deal with a lot of time of use rates yet.
Yeah, we don't either.
I feel like that trend is going to be changing real soon. Another point to make: if you're going to model based on time of use rates, it's really important that you have detailed load profile data.
Oh, that's thank you for that, and that's very true. Because obviously when we have estimated load profile data, we don't really know exactly when our system is using electricity perfectly, but you can actually input hourly data into this system. So let's see if we can find a fun one here that's a little different. See what that one says. Oh, that one's not quite very different, is it? So I was trying to find a little different one, but let's see if we can find a small business one from Omaha Public Power District, which is one of Nebraska's utilities. And so we'll just pick on them a little bit, and we'll say maybe this is a general service. Let's do small demand, see what that says. General service, small demand, which might be a small commercial type of system. And this one is I wouldn't say it's time of use, but what we have is a 2-period rate structure, where it's a summer winter rate structure. 6 cents for the first 300 kilowatt hours, almost 4 cents after that. You recognize these rates are very, very low, 6 and 7 cents. But what we're not getting here yet is that there is an additional detail, which this is a demand rate structure, where if we scroll down, they're also getting charged $5.38 for every kW above 18 kW. So if they go above 18 kW, they're getting this pretty significant charge. But what's important about that from a solar standpoint is that solar may not reduce this demand. And so then when we model this system, if we were to model this system with this rate structure, and let's just go ahead and try this for fun. We're going to model it with this rate structure. One thing we need to add in, let's just put in a number here, 0.05. That's 0.05. And we're going to put that number in for our cell rate.
0.55.
Yeah, 0.55. So we'll have our cell rate be the same. My button's wrong there. Okay, and then we're going to do this with net metering plus dollar credits, which is about what we had before. And now we're going to go ahead and run this simulation, and we're going to find that this is, let's go back to summary, this is not going to look good. And it doesn't look good for, these things all look the same, but what happens is our electricity is so low value. It was 12 cents, now it's 6 and 7 cents, and our paybacks are just really poor. Our net present value is negative, even with 100% debt fraction. So things don't look good, and that's where some people will say, well, the best places for solar are the places that have lots of sun, like the Southeast United States, New Mexico, and Arizona. And said, well, that's true, but when we look at economics, the value of that electricity is so important, and that's where a system in Ohio or Michigan looks a lot better than a system in Nebraska from an economic standpoint, even though Nebraska gets better sunlight. I guarantee you that my number for kilowatt hours will be better than theirs in Ohio for the same size of system, because I'm in Nebraska and they're in Ohio, but their electricity prices are higher. Their system's probably going to have a lower payback and a higher net present value than mine. So a little bit of a challenge we face, but also one that's really important to think about, where value of electricity is critically important. I'm pretty much done with what I wanted to share. Or if we have any questions, we can jump to that.
I think we could take some questions, and if there's no specific questions, I have 2 more things. I'll throw some questions at you, John. I'll make it work for the last 15 minutes here. So first, we'll open it up. Are there any questions for anyone on the call? If so, feel free to unmute yourself and ask, or raise your hand, or type in the chat box.
I'm going to try to put our rate schedule back to where it was here.
43351 is the zip code. That's the wrong one.
Oh, that's the wrong one.
Yeah. There you go. That GS1 up top there.
Secondary GS1. Okay. That's going to get us pretty close to where we were at. And well, actually, this is one with a with the demand rate. Okay.
So, and I don't know.
That's fine. No, that's no problem. We got questions. Let's go to that.
two things. Okay, so there's a question from John in the chat box that says cost of software or system. I'm not sure if I understand the question.
Yeah, I think I'm going to try to answer it and see if this is the right answer, but a solar array is made up of component parts of the solar panels themselves, the inverter, and that's pretty much, and then maybe a disconnect, and then the wiring and stuff in between. The inverter has software, and that inverter software is basically updated wirelessly to the inverter from the company. If it has internet connection, you can do software updates with a disk by calling them, and they'll send you a plug-in. So those software updates are part of the initial purchase price. Most solar companies have software for monitoring that is free, but sometimes they'll have costs if you want more detailed monitoring. Enphase is one of them.
John, he says, I mean the cost of the software package you're describing here. So, John,
go ahead.
Do you mean the system advisor model?
I think that's what he means.
Okay, the cost of the system advisor model, yes, is his question. So yeah, the cost of the system advisor model that we've been demonstrating is free. So this is a tool, again, that's been developed by the National Renewable Energy Laboratory with funding from the Department of Energy, and it is a free download for anyone. Yeah. So you can log in using the link in our I think we've included a slide in all 4 sessions, and that'll take you right to the page where you can download it, John. Two of the other things I was thinking you could show them quick, John, since we have a few minutes. One was to maybe look at, how we can be a little more advanced with how we account for operations and maintenance, specifically with inverter cost. And then the other thing that I think might be a good takeaway and maybe a closing activity is to just show how simple it is to download a PDF report. So I do that a lot when I'm working with farmers and lenders, and we do some modeling, and we get done, and you can just create a simple PDF that shows a lot of the highlights around the assumptions and the results that I think is pretty useful.
Very good. Here's the system advisor model, and really the reason it's free is that it is a federal government funded program, and they've been able to get grants from the Department of Energy and other things to keep this funded. And so that's why it is a free product. The National Renewable Energy Lab is who created it and maintains it. And there's the SAM model website. It's just sam.nrel.gov, and you can go to download.
And one thing to point out, John, I don't know how many years we've been working with this program, but it seems like the better part of the last decade. They do a really good job of maintaining it. And, there's constantly new versions that are coming out that are adding additional features, fixing, hiccups or bugs that people have identified, just making the user interface easier. So it's something that has been around for quite a while, and they do a really good job of pushing out updates.
Very good. So if we were trying to account for O&M differently, and so there's in this case we have a fixed O&M of $15 per year, and remember that was costing us about $300
per kilowatt per year.
Excuse me, that's what I meant, per kilowatt per year. So that's ours is a 24 kW system, so 15 times 24 is what we're paying each year, and we don't have an escalation rate on that right now. But sometimes the reality is that we can think about this a little differently, and we can put values in. This is in dollars per kilowatt, so maybe we want a lower value for the first few years, and it could be as low as 0. And so maybe we have 0 for 10 years. And then what we're worried about is an inverter replacement. And an inverter for this particular system might cost about $3,000. We could simply put an inverter replacement in year 10. And now we can go ahead and simulate. Now our numbers aren't going to be quite right because our electricity prices aren't right. But in this case, now we have an O&M of 7. Oops. I did that wrong.
Somebody punched the wrong button.
See, that's what happens.
And this is the reason I point this out. We actually have a couple there's a couple of installers in Ohio that I've noticed have, they've done this where that's per kW per year is the reason there's.
Yep, I was just going to figure out what I wanted it to be.
Go to a fixed annual cost and do your so it's the top one.
Oh, fixed annual cost.
Yeah,
I could do that.
Per kW.
So, let's get back on the right screen here. So we're gonna make that 0 and hit cancel. And our fixed annual cost, where instead of a value, let's do this in year 10, where we had a $3,000 thing, and then it would show up, right?
Just double check that you don't have 72 in that fixed cost, because you hit cancel. I'm not sure if you needed to hit OK.
I think I hit OK. 72.
Yeah, that's still there. That needs.
Oh, there you go. You're right. In the 72,000, you meant.
Yeah. So hit OK. There you go.
Now, when it models that and gives my cash flow, I'm going to have just this $3,000 fee here in year 10. Now, I think that's fair to do. Whether you're going to have that inverter replacement or not, it's up in the air. There are some inverters with 25-year warranties, and you could try to value that a little bit. What I try to tell people about O&M is that O&M is low, but it's not zero. And so if, in the case I had before where we had $300 some a year, well, you're not necessarily going to spend that 300 every year, but you might get in year 5 where maybe there was something happened and something needed replaced, and maybe some mice chewed on the wires, and you had to have the installer come out and do some work, and you had to pay him for that. And all of a sudden now you have some dollars that you accounted for in your cash flow. And so I think that's where that O&M is important to think about. It should be something. It should not be zero. Just like inflation, we could say electrical price inflation should be something. It should not be zero. Well, the electric company says, well, I didn't change our rates for 10 years. But then you change them by 12%. Well, now what we could do if we wanted, we could model that with the 12% every 10th year. It's just a different way to do it. I'm not sure what's right or wrong. The system does allow us to do that sort of thing.
And that's where it's important to look at what the values are in a cash flow table. And the other thing you could do with O&M is a combination. So maybe you say, well, we're going to start real low and apply $2 per kW annually with a 2% escalation. And then you have your fixed cost in year 10 that says, we think that's when the inverter, cost might hit. And then, you could get an even more detailed perspective on system cost.
Right.
Operations and maintenance costs.
So let's run let's go back to our aggressive scenario, and we'll just run in this, if we click on this, we can run a report, create a report, and it creates I didn't have a scenario or a weather file selected. So I'm going to create the report, and it's going to create a PDF report. So we'll go ahead and just put that right there, and then hopefully we can find it. It's opening it in my other screen here, and then I'll pull it over once it gets open. And it created a PDF report that then I can just send to a customer.